Okay, let's start today's course. Last week we have talked about that, like around 10 years ago, we almost uh, solved the machine translation task, and we use a neural machine translation to get all those things done. And the neural network we use is kind of like a recurrent neural network. Uh, and uh, and our next step is to make those translator can be deployed on our mobile devices, on our edge devices. So several efficient neural machine translation methods have been proposed, like the left transformer, which can reduce the model size by tuning and quantize the parameters in the machine translation models. And our next, another big breakthrough in the natural language processing is definitely the large language model. It's not just a breakthrough in natural language processing. It's like the king in the AI domain. So basically, uh, we would like to highlight that the most important capability in the large language model is that it has zero shot or few shot learning capability, right? Basically, we can use some human prompt to just ask some questions to the large language models, which they never seen those kind of question before, but they can answer those questions correctly. Even they cannot. This called zero shot questioning and answering task. And if they cannot do it like a completed this question and answering in the zero shot manner, we can use some examples as a prompt for the large language model. And surprisingly, by adding some examples to the large language model, it can increase the probability, the likelihood of using the large language model to handle those kind of problems. This is called few-shot learning capability in large language models. This is the most like attractive property in the large language model. And because the OpenAI, like the 5 years ago paper, they proposed that large language model can be used as a zero shot or few shot learner. And this paper start the new era of AI, of large language models. But we can guess from the name, right? It's called large language model. So like the cost must be very hugely, and it comes at a cost of those large language models. We can say even in like around 5 years ago, those large language model already have hundreds of billions parameters, right? There's 175 billion parameters is in the GPT-3 models. And now we are using GPT 5.2, right? It's involved for like multiple rounds, right? So, because like GPT-3 is the only open source tech report from OpenAI, so we cannot know the exact number of nowadays we are like widely use the GPT. What's the parameter number in the GPT 5.2? But we guess that it should have trillions numbers of parameters in those GPT 5.2 models. And I heard like there are some big companies are trying to train the latest like a large language model with 10 around 8 trillion parameters. I think that's the most state of art large model in the on the market. And another powerful module in the large language model is the chain of thought. The chain of thought can help the large language model rethink their output, right? It can make it thinking like our human beings. Like we think for the first round and maybe turn off our first round thinking and have our second round thinking, right? This is our human beings tackle those long horizon problems, right? This is our manner. So basically, this chain of thought thing is to make those large language model have those thinking capability. This is a very important module in the large language model. But like as I said, like a large language model, like considering the model size is already have lots of number of parameters, right? And for the output process, if we want it to generate some answers, it's also because it have a thinking process, right? For the thinking process, they need to generate those sentences, those paragraphs, right? So even some articles, right? For example, you use those ChatGPT for deep research, is like just generating a whole article, right? So basically, like even you just want to get a very short answer, the thinking process also costs lots of generation, computational resources, right?
In the given or like answer given in the form. So the model tries to verify those answers, like by using this output.
Uh-huh.
So, or it's kind of like try to mimic the answer.
Uh, uh, it's not like mimicking, it's like the thinking process. It first generates those channel thought things, the thinking process, like they have 3 plus 6 equals to 9.
Like this, it's kind of like following the example.
Uh-huh.
So, like how we are like sure that this is the unique thinking process, not just copying the same process or algorithm it gives in that answer.
It's a new processing process. And basically, our large language model is becoming like larger and larger. We have like a initially it have hundreds of billion parameters. We call it large language model, but nowadays our large language model have thousands of billion parameters, thousands of billion parameters, right? And but our computational resources, our computational devices are involved not that fastly, right? For example, initially for deploying those parameters with hundreds of billion parameters, we need to, like in 5 years ago, our state-of-art GPU is NVIDIA A100 GPU, right? H1 A100 GPU have around 80 gigabytes video RAM, right? So for deploying those 100 billion parameters GPT-3 model, we need at least 4 A100 GPUs to deploy just one model, right? But when the GPU when the model goes to around 500 billion parameters, it needs more than 8 A100 GPUs, right? But for computational node, for like standard server, normally the maximum capacity for like installing the A100 GPU, like the maximum is 8. So like even for one node, like if we use the very straightforward deployment method to deploying those model with 500 billion parameters, it's not doable, right? So it's very like a complicated engineer process to deploy those large large models cross node, because if you split the model into different parts and you allocate those parts in different node, the node has like a lot of I/O latency, right? Because it's not between just the same devices. The I/O is very costly, and the latency, especially the latency, is very costly. It's very high, right? Because if you want to realize just the inference, I mean, let just the inference, you need to input your data into one node, and after one node generate some latent, some intermediate activation. You need to transfer the intermediate activation matrix, the activation feature map to other node, to another node, and then it needs to transfer back to the node. So the communication makes the whole inference process very very high. And this is just for inference, right? For training, it's more complicated, because for inference, we can use 2 nodes, we can use 3 nodes. But for training, we need we need a huge batch size, right? So normally for training, we use like thousands or tens of thousands GPUs. So it needs thousands of nodes. And the communication between thousands of nodes is another problem, right? There is a distributed processing problem, right? It's very like complicated. Even for those big companies, they has a very large team to handle those distributed training problem, right? But yeah, uh, anyway, with at that time, like under the constraint of the model size and the computational devices, the deployment, no matter the training or the inference of large language model, is really a big problem. And even nowadays, our GPUs improved. We have H series GPUs. Yeah, I think for the H200 GPUs, the VRAM is around 140 gigabytes. It's slightly better, but cannot handle those problems, right? Those because the model size increase like a exponentially, right? But the GPU's the GPU computational capability just increase like linearly, right? And nowadays the state of art GPU is GB series, GB 200 or 300, and each GB 300 and a GB 200 node is like millions dollars. Like there's quite famous demo is that for the A100 GPU node, like in 10 years ago, Jason Huang signed his name and delivered the first A100 node to OpenAI. And in 10 years, like in last year, it's like he signed his name to the latest GB 200 server and delivered also to OpenAI. But still, the gap between computational devices and the model size is a big problem. That's why there's a new like a topic called AI infrastructure, and Like efficient AI is also they have some overlap between AI infrastructure and efficient AI. And an important solution for making the large language model efficient is the sparse attention, uh, like techniques to because I have mentioned that uh, the computational cost in the transformer is quadratic to the number of tokens, right? Because it have a like a self-attention layer in the transformer. So the computational cost of large language model is quadratic to the number of tokens. And for processing a long sequence problem, and the cost will be like super huge, right? But if we can make the activation, those self-attention layer in not quadratic, just linear or n times log n linear to the number of tokens, it will make the whole large language model inference more cheaper, right? So the most intuitive solution like it's a sparse attention. It's to making those process more sparse, and this can make the whole process like a n log n like linear, not quadratic, right? And another thing is that the importance of running LLM on edge, because like uh, deploying those large language model on edge is very useful, right? For example, we hope to run our for example, those Copilot service on our devices locally, right? To avoid those information leakage, right? So, for example, I think this is widely used. Those locally used Copilot service is widely used by those law firms and those like financial consulting companies because there are some law and their customers do not want their information be uploaded to the internet, even though not so many people can access the data in OpenAI, right? But definitely they do not want their information be uploaded by some consultant, by some lawyer to their commercially daily used GPT model to ask the question based on their personal information, right? So it's very important for those like law firms and the consulting company to deploy their locally used like a Copilot service. So ideally is to deploy those on some laptops on some like local servers, right? And another example is that if we like eventually we hope like we do not just have those digital assistants, right? We hope we can get some physical assistant, like some real robot can help us to finish some daily labors, like help us cooking, help us doing laundry, doing the like clean the bedroom, those tasks, right? But like the brain of those robots should be very large scale models, right? Nowadays we have those like those vision language action models can serve as a brain to control those robotics, but Definitely those large scale models are uh, it's not very deployable to those robotics. So we need to make those models smaller, can be deployed on those edge devices. The most promising solution is the large language model quantization techniques to quantize the models. Basically, this is the most straightforward solution, right? Because uh, initially those large language models, the weight in the large language model is represented by some four position numbers. Like in computer science, we use some float number to represent the weights in the large language model, right? So for every weight, it need to be a 32 bits number, right? So it's normally cost like 8 bits to store just one weight, right? But if we can quantize those 32 bit with to maybe 8-bit or 4-bit, we can save the memory cost around like maybe 4 to 8 times, right? This is the most straightforward solution. And the the most intuitive algorithm to realize that is to run some round to nearest. We can just clip the redundant like flow number from the numerical is we can realize that, but it will make the quantized large language model lose the performance of understanding the content of generating the language. So there are many popular advanced quantization algorithms are proposed to solve this kind of problem. Right? The smooth quant and the AWQ, they all from NVIDIA, uh, and they all interrogated into NVIDIA TensorRT toolbox. Basically, if you train your own large language model or you fine-tune your own large language model, and you want to deploy those large language model on some real devices, you can just feed your weight to the NVIDIA TensorRT toolbox and choose those algorithms smooth quant and AWQ. Like all AWQ, you can get the quantized large language model. And definitely, this is just a brief review about what is large language model quantization. We will talk about more details like in the following class. And also we have those many open sourced uh, like package have been released, like the Tiny Chat is a lightweighted large language model inference engine, and like basically we can compress the large language model into a smaller model and make it can be deployed on some edge devices. Those NVIDIA Orin is smaller, is a very small deployable edge devices, and it only have around 10 gigabytes memory, and the computational capability is also very limited. But by using some compression techniques, we can deploy our large language model on those mobile devices, on those edge devices. And there's another two very famous large language model deployment inference engine is the VLLM and the SG long. they're all very famous and uh, like based on those two toolbox, two open source toolbox, and the founder of those two toolbox, they all founded their own startup. I think like one of them is within just half year is already been like a unicorn startup, raised like the estimated price is more than $1 billion. So this is a like a have like a very high commercial profit making this large language model deployable. Oh, uh this is the Orin. It's very small NVIDIA edge devices. You can deploy those smaller model on those Orin. And I think many autonomous cars use these kind of chips to deploy on their cars for their autonomous cars self-driving system. But Tesla didn't use this chip. And basically, we can use those toolbox to run the large language model on the edge. And also quantization, the solution quantization, for example, those AWQ can quantize those large language model to 4 bits. 4 bits compared with like a 16 bits is like a 4 times compression. And it can also bring like around 3 times speed up. For example, to deploy a 7 billion parameters model, those Llama 2 model on a 1490 customer usage GPUs. Basically, it like can generate like around 200 tokens per second. Like you cannot feel any latency. And definitely like some people want to deploy those large language model on the mobile phones, right? For example, recently there's a very famous demo called Doubao phone. Like they can use a large language model as an agent to control your whole phone, control your phone, and you can just use your language as a prompt to those large language model agent. For example, you can say just help me order a flight ticket to Los Angeles for next week. You should choose the lowest price over several app, right? And the large language model as an agent, they can control your phone and open several applications and search the flights individually and listed all the options and choose the cheapest one fit your requirement. And like eventually, like we hope to deploy those large language model agent on our phone itself, right? We do not want to like upload our like all the information to the cloud to the server, right? Like ideally, we hope it can be deployed on the phones, right? But still considering the efficiency, considering the latency, we still have a big gap between using those agents on the phones. And yeah, basically we have talked about what's the state of art of deep learning on computer vision, on large language models. They all have very promising, very like existed like state of art models. And the next topic I want to show, or the next breakthrough I want to show is in the multimodality domain. Like well, so basically we first want to understand to uh talk about what is multimodal, what multimodality. Basically, besides like a language, like a language only and computer vision only, like uh, all the modality can be seen as a multimodality, right? If you combine large language and computer vision together, is multimodal. And if you consider audio and language, it's also multimodal. If you consider uh, audio plus video is a multimodal. Basically, like many data format can be considered as a multimodal. But before the large language model, before deep learning, those multimodal have less breakthrough, have less achievement because like we do not have enough tools, we do not have enough algorithms to analyze those multimodal data, right? But within recent years, everything changed. We have those vision language models. For example, the Lava model can achieve the general purpose vision and language understanding task, right? Basically, this is a uh, 2 years ago model. This is the first open sourced multimodality large language model. I have stayed in the Lava team for about half a year in 2024. And basically, what's the function or what's the Lava model can do is that if we feed it not just the language, but also we can feed it a image into the Lava model, and we ask, do you know who draw this painting? And the model can answer this language plus uh, image input task, right? And this is very big breakthrough in 2023. And in 2024, every company is starting those multimodal thing. And I think like for 2025, every like mainstream large language model have those features, those multimodal features, right? And for those multimodal thing, I as goes further within recent 1 year, we have those it cannot only just read image and language combination. It can also for some models it can understand audio input, right? You can chat like uh literally chat with your like Gemini model, right? With your ChatGPT model, and you can those Gemini models can understand even audio videos, right? It can if you feed some like a uh, uh some YouTube links to the Gemini models, it can help you understand the video on the YouTube, right? On the YouTube, normally it's very long video, right? Like hours length videos. It can understand that. And like for some models, this is just a multimodal data in, right? It can understand the input in different multimodality. And for nowadays, they also have some multimodal out model, right? For example, those model can output some audios, can chat with you, and it can, for some models, it can even generate some image as their answers, in their answers, right? So basically, multimodal understanding and generation is a new topic in the uh, in our large language model domain. But this all because of those deep learning. So this is a very big breakthrough in our large language in the deep learning domain. And here is one example of the multimodality large language model. The VLA model is trained by NVIDIA research, and like the high level idea of this multimodality large language model is that we train a projector layer and we basically transfer the variant signal to some also to tokens, right? And we like fine tune the large language model to make it can understand those variant tokens, and then we can like enhance the large language model into a multimodality large language model, because we can use this vision encoder plus projector and fine tune the large language model to make it can understand the multimodality input. And also this is also very big, very brief discussion or review about what is multimodality large language model. We'll talk about this topic later. And definitely like this, like the same pattern is that after we can realize this capability, we hope to make the vision language model more efficient, those multimodality large language model more efficient, right? So there are several, I think there are like many solutions to make the multimodality large language model more efficient. VLA is one example. Basically, they use some polling algorithms to like making those variant tokens smaller so that it can make the whole understanding more smoothly. Here's some examples, demos of the VLA model. And by using those, if we can, by like including some network compression techniques, like we can make those lava model on device. For example, we can run those VLA model on some MacBook, and nowadays they have some like OLAMA application on the not just on MacBook but also on the Windows PC, right? It can help you deploy your those relatively smaller model on your own MacBook or your own PC. And another thing is the robot control, right? We have nowadays we also have those vision language action model, right? Basically, the vision language action model is based on the vision language model, and we use those vision language model as the brain for the robotics, and when it can understand what and precise the whole status of current base, and it can generate some action to control the robotics, right? But nowadays, for those, if we deploy those very large like vision action language action model on some hardware, on some robotics, we can only run it around 3 Hertz due to the high computational cost and the networking latency. So many researchers within recent 1 year have focusing on making those vision language action model more efficient. And they have another like a deep learning also have like a lots of uh like a achievement for other domains like deep learning for games. Like in 10 years ago, we have those AlphaGo, right? It beat the top the top Go player like in 10 years ago. And at that time, they use around 2,000 CPUs and 200 GPUs to to train or to inference their models, right? But with the help of efficient AI, with help of the construction of some like AI infrastructure, nowadays, if we still want to train like those AlphaGo algorithms in 10 years ago, basically we can realize those within like several A100 GPUs. That's okay. So we can say that so like those efficient AI, those AI infrastructure indeed help us demonstrate democratize those AI algorithms for many domains, right? And another achievement by deep learning is it can help us for scientific discovery, right? For example, the most significant example is those AlphaFold model, right? Those AlphaFold models proposed like 7, 8 years ago, and for last year, no, for 2024, it's the team of proposing AlphaFold winning the Nobel Prize, right? And for Nobel Prize of chemistry, right? And the the author, the last author of those AlphaFold paper is Demis. Uh, Demis is the founder of Demand, and now he's the president of Demand at Google. He's leading the whole Gemini thing at Google. But like in 8 years ago, those AlphaFold model, they still need lots of computational resources. Like for 8 years ago, it required around 100 TPU V3 course for few weeks. Right now, 100 TPU is also doable for academia research labs, but at that time is very costly. For the deep learning development, basic if we look it back, we can see that they have three um, orthogonal pillars for the deep learning development. First pillar is the algorithms, right? They have so many brilliant men who have proposed many algorithms like deep learning algorithms, the back propagation algorithms, the ResNet, the attention is all you need. All those papers can count it as a algorithm contribution to the deep learnings, right? And another pillar is the hardware development, right? Especially within recent 10 to 15 years, right? Our like a GPU, some researcher finds that those GPUs can help us accelerate the whole deployment, no matter training or inference of neural network, right? And many researchers are trying to squeeze the computational capacity in those GPUs. And in the meantime, NVIDIA and AMD and Google, they all trying to release their more and more powerful GPUs, right? So that's the second pillar of the deep learning. And the third pillar is the data. And in 15 years ago, we have those image nets. Is at that time it's very challenging, but it shows that like we can use like those data to train those large scale models, and uh this is a kind of like a once for all solution for many challenging tasks, and this is a good like a oracle for our AI researchers, and it initiate the whole computer vision flourish, right? And within recent 5 years, those large language models thing prove it again, right? Like they collect basically any like sentence in the world on the internet and train those large scale language models, and the performance of those large language models are amazing, right? So basically, the data are the third pillars for the achievement of deep learning. And like this is the third pillar for the development of deep learning, and we also have considering the efficient AI, like nowadays the most standard, most acceptable like data format in our in deploying those large language model is A-base data format or 4-bit data format, right? And our large language model, the architecture is uh, transferring from dense architecture, some quadratic self-attention layer to some sparse attention layer to some linear attention layer, and the even though the model size are becoming larger and larger, the computational cost, the price of generating the tokens is uh, increasing not that crazily, right? So uh, we can say that the model, like those efficient AI effort make those large scale models more accessible to our customers, right? And definitely there's like a lot of software innovations important. It's important in advanced technology node. Like in 10 years ago, our uh, like those devices are formed by those 7 nanometer like technology, right? But nowadays our uh, those GPU chips are produced by those. I think right now is 2 nano meters technology, and those like by combining those hardware, physical, like all those technologies, we can make those chips doable and make the AI devices also more capability to handle those large scale models. And Definitely, those hardwares improve a lot, and we have those like 10 years ago, the most state-of-art model is the V100, and in 5 years ago we have the A100. 3 years ago we have the H100, and for today we have like B100 and GB 200, GB 300, those GPU devices. And definitely those edge AI hardwares improved a little bit, right? Not significantly uh, because we can build our GPUs larger and larger, right? Because those GPUs normally are deployed on some cluster centers. Those cluster centers have enough powers to power the cooling system, to power the fans for the GPUs, right? So basically, we can increase the chip size, we can increase the cooling system, we can like without any like with less limitation, right? But for building the edge AI hardwares is hard, right? Because uh, it's not that easy to increase your the chips in your mobile devices, right? Because even you increase the size of the chips, the heat will become a problem, and you cannot increase the cooling system in your mobile devices, right? So this limited, those space limited, those like physical limitation limited the development of those edge AI hardware's development. And nowadays, Apple is trying to like have the neural engine chips, right? For example, their M series chips is very easy to deploy those AI models on their mobile devices, right? I think many people use their those smaller Mac to deploy their local chatbot. And also, NVIDIA have their Jetson edge devices, right? So as I mentioned, they have those Orin series. Nowadays, I think is Saw, and for Saw is more advanced, and I think, but for definitely for the Saw is more expensive. Right now, for the Saw, just one Saw chip is around 3,000 dollars to just buy one edge devices. And considering the edge devices, the most like extreme edge devices is the macro controllers, right? Like they have some researchers and engineers and trying to deploy those large scale models on all the AI models on those microcontrollers. They also want to train their or fine tune their AI models on using those microcontroller. It needs lots of engineer effort to make all those can be done. So basically, we still have a huge gap between the edge AI and the cloud environment. For example, for those cloud AI, like for the H100 or A100 GPU, it have 8 GB VRAM, and the storage is TB level or PB level, right? But for mobile AI, like the memory is around 4 GB, like at most like 10 GB, right? And the storage is also limited. And for the move forward from like mobile AI to tiny AI, the memory is very limited. Is only within one megabits. So for the current landscape of deep learning, uh, normally it's need lots of it's consume lots of computational resources, and for realizing those large projects, many engineers and researchers are involved. For example, OpenAI, like as a startup, I think OpenAI nowadays have around 6,000 people involved in OpenAI, but definitely not all 6,000 are training their ChatGPT models. But still a huge team for maintaining their huge project. And definitely for nowadays, those AI project, it requires lots of data. You need to collect from the internet. You need to clean those data, can be used, can be fitted into the model training, right? But for those tiny machine learning things, it's like the whole logic and the whole landscape are totally different, right? Because for the tiny machine learning, we only have we have less computational resources. We need to like cost less power to impart to run those models, to train those models. And uh, we have fewer engineer works to do, and definitely we have less data to train the model. So it's for those tiny deep learning, for those efficient deep learning, we still have a big gap between the state-of-art large scale model study. Uh, yeah, so definitely this is the high level landscape of our class. We will talking about on the one hand, we will definitely talking about the state of art large scale models. Like we will in the following class we will cover the generative models. We will cover the large language models. We will cover the different models. And also, after we talk about those still art models, we are talking about the solution about making those still art models more efficient. And yeah, for our final project, it will around those efficient AI things. It will around those large scale models, and you will find some papers, find some relevant project, and like solve it. Yes. Okay, this is today's class. Let's wrap up.